Good morning, dear students. Today we are having the last practical lesson of advanced calculus, and this lesson will be about a trigonometric Fourier series and how it looks like. So the general form of trigonometric Fourier series for 2p periodical functions is the following. So this is the zero term divided by 2 plus sum from 1 to infinity an multiplied by cosine of nx plus bn multiplied by sine of nx. And how to find these terms, coefficients of this series. So a0 can be found as integral from minus p to p of this function divided by p. An is integral from minus p to p product of a function multiplied by cosine of x, and this integral is divided by p. And for Pn, integral from minus p to p of a function multiplied by sine of nx. And this integral is divided by p as well. What about 2L periodical functions? We will talk about them later. So now let's have some practice with 2p periodical functions. Any questions about this theory? Okay, if no questions, let's start. So we will have to expand the following function into Fourier series. So the expression for the function is the following, and this function is given piecewise. So if from p from minus p to 0, it has value 2, and from 0 to p it has value -1. So we know that a function can be expanded into the Fourier series if it's periodic, and we will continue this function on the whole on the whole numeric axis, and it looks so the following. So the following appearance of the graph. We won't draw it from the beginning, so we will not draw it. We will just look at this graph because plotting consumes a lot of time. So actually this function, so this fragment is for this expression that is given analytically, and then we continue it to the right side and to the left side. So how it works? So we continue the function periodically. Let's find the coefficients first of all. So a0. So how it would be found? So we will use the following formula. So from minus p to p, or integral f from x dx. And as this function is given piecewise, so we will split it to the sum of integrals. So what we will have, so 1 over p, so integral from minus p to 0 of 2 dx, and minus integral from 0 to p. And now substituting. So doing the substitutions. So what do I have here? Okay, let me move to here. So 0 minus p, so it will be p. No, the 2p. 2p and minus p. So actually I have 1 here. Wait, so this is so the answer, so the term a 0 equals 1. Let's find an. So now we will multiply this function by cosine of nx. Actually, we're doing the similar stuff. So cosine of nx, and here cosine of nx as well. And what we will receive actually. So finding the antiderivative, so 1 over n sine of nx with the substitution from 0 to minus p. From minus p to 0. And here as well, the same expression, but other substitutions from 0 to p. And actually, what can we see here? That so sine of 0 is 0, sine of pn is 0 as well. So an equals 0. So all an terms. And what about bn? Let's calculate them. So here will be sine of nx. Here as well. So sine of nx, and here sine of nx as well. So finding antiderivatives. So minus 2 over n cosine over nx and minus plus 1 over n cosine of nx. Yeah, and forgot about substitutions here. So with the substitutions from minus p to 0, and here with the substitutions from 0 to p. Now providing these substitutions. So 1 over p, and here, so minus 2, so 1 minus cosine of pn, and here, let me also move n out of brackets. 1 over pn, and here plus 1 cosine of pn minus 1. Okay, let's okay, now let's expand brackets. inner brackets. So I will have minus 2 plus 2 cosine of Pn plus cosine of Pn and minus 1. So I will move 3 out of brackets here. So 3 here and 3 cosine of Pn minus 3. Oh, cosine of Pn minus 1. And by the way, how can we substitute cosine of Pn? Actually, cosine of... so what does cosine of Pn equal? So if n is even, so the cosine of Pn equals 1. If it is odd, cosine of Pn equals minus 1. So how can we write down it here? So we will replace cosine of Pn with minus 1 in power of n. And then, we will do the following stuff. So we will try to simplify this expression. So if power of n is even, what we will have? We will receive 0. So it will be 1 minus 1, so 0 if n is even. Or I can write it down like n equals 2k. And if n is odd, so it will be equal minus 6 over Pn. And n is odd, or I will write it like 2k minus 1. So that's what we received. Let me check this Fourier coefficients. Yeah, they are correct. And then we have a0, we have an, we have bn. So let's substitute them into the Fourier series. And we will also mark, so we will replace function f from x as the sum of the series. So it will be the following. So a0 divided by 2, 1 over 2. And so what to do with the sum? I will move. Okay, let me leave it like this for now. So minus 6, minus 6. Okay, let me move minus here. 6Pn sine of nx. But as we know already that if n is even, so it is 0. Stop. Yeah, not correct. So what will we do? So we will replace n with this expression, 2n minus 1, and here 2n minus 1 as well. So why are we doing this? Because we will simplify this expression. We will know that n n coefficients are always odd. And let's also replace, so let's move constants out of the sum. So what I will do here, I will move 6, I will move p, and let's move a sign into the numerator, and I can remove brackets in the denominator. So this is the Fourier series that we received. So no, s from x, so sum of the series O equals f from x at all points where function f is continuous. And what about discontinuity point? So discontinuity points such as 0 and p minus p. So let's calculate s at point 0. It will be received in the following way. Yeah, so we also have to find the sum of the series at each point. So f from 0, or f from plus 0 plus f from minus 0 and divided by 2. So f from plus 0 equals minus 1 and f from minus 0 equals 2. Dividing it by 2 and we received 1 over 2. And what about s from p, s from minus p? Actually, they are the same. So f from p plus 0 plus f from p minus 0 over 2. So f from p plus 0 uh, equals 2, and f from p minus 0 equals minus 1. So the answer is 1 over 2. And actually, this is the full solution. Let me check in. Mhm. Yeah, so actually, yeah, so it matches all nodes. Any questions about this exercise? Okay, I guess that no questions. Okay, let's move to exercise 2. So what we will do here? We have to expand given 2p periodic function f from x equals x squared into Fourier series, and with the received result in Fourier series, we will calculate sum of numerical series. So it is the task for application of Fourier series. So actually, the main application of Fourier series is to approximate the function on at the segment, but also we can use them to calculate sums of numerical series. Okay, let's calculate. Let's expand this to be. Let's. Uh, okay, we will not plot this graph of this function. They are here. Okay, I will can show how to plot it. So y equals x square, and I will write down that uh, so x from minus p to p. Uh, ah, so now it is okay. And now I want to move it. I want to continue this function. So how to do it? So let me use. Okay, so let me go from. So I will shift the graph left, and this bounds also are shifted to left by the period. Stop. What's going on? Why? Ah, 2p. Yeah, I must shift by the period. And let's also draw plotted here. So minus 2p, and here will be from p to 3p. So that's how we plotted this curve. So we can do like this. Okay. So plotted the graph. So let's look better at this graph because it looks beautiful. So here we have yeah, so points so 3p minus p p and 3p. So we see how the function f from x is continued periodically. So now let's calculate coefficients for this function. Actually, because function f from x is even, so x square, it is even just so we know that function, so the square function is even. So in this case, Pn are 0. So all coefficients Bn are 0. And what about coefficients An? So we will calculate them so in the following way. Yeah, okay. So first of all, A0. So we know that coefficients are calculated in the following way. So from minus p to p, f from x dx. But uh, because the function is even, we will simplify it a little bit. So we will do like this: 2 over p, and integral from, we will integrate just from 0 to p. It will be enough. So let's calculate. Okay, let's calculate. Yeah, so we will receive, yeah, here we will receive x, let's substitute x squared dx. And it equals 2 over 3p x cubed from 0 to p. And it will be equal, so multiplying by p cube. So it will be equal to p square over 3. So received A0. And what about AN? Let's calculate them as well. So AN will be received by the following formula. So we will multiply by cosine of nx, the function f from x. So uh, this integral will be calculated by parts. So let's do it. So u equals x square, du equals to x dx, dv equals cosine of x nx dx, and v equals 1 over n sine of nx. And now let's substitute everything. So first of all, product of u and v. And with substitutions from 0 to p. So first of all, we will write down everything, and after that we will simplify. Yeah, minus 1 over n. Here will be, oh, I can even move 2 here. So v du. So x sine of nx dx here. So what can we simplify? So here, so we have sine of nx, so we will have sine of Pn and sine of 0. So this part will be eliminated, and we will have only this integral. So minus 4 over Pn and this integral. And now as well we will integrate by parts once more. So u equals x, du equals dx, dv equals sine of nx dx, and v equals minus 1 over n cosine of nx. So receiving the following expression. So first of all, u and v with the substitutions from 0 to p. Plus integral from 1 over n. So 1 over n integral from 0 to p cosine of nx dx. Okay, now let's calculate everything that we have here. So if I substitute p here, I have so minus 1 over n p cosine of n of pn. And if I substitute 0, I receive 0. So that's all what remains from this part. And what about this integral? So 1 over n square sine of nx with the substitutions from 0 to p. Of course, this part will be equal 0, and what we will receive the following stuff. So 1 over p n. Okay, so let's multiply everything. Oh, okay, yeah, and 4 here. So 1 over n and multiplied by minus 1 in power of n. Okay. And p, lost p. So what do we have here? We can cancel p, and we receive 4 over n square multiplied by minus 1 in power of n. So this is an. And now let's write down the Fourier series that we received. So s from x equals so p square over 3 and plus the following series so minus 1 in power of n over n square by cosine of nx. And what about 4? I will move it out of the sum. So this is the series that we received. It is always continuous because the function is even. It is continued in the even way. So we received the following series. And how to how to calculate numerical series that we have to calculate. So let us look at this at this part and at this series. Something is similar. So uh, uh, how to receive, for example, S1? We can substitute x here instead of so we can substitute 0 instead of x. So we will calculate the value of this sum at point of so we'll calculate this sum at point of 0. What we actually know? Yeah, we can also write down like f from x. So f from 0 equals 0. Yeah, so f from 0, okay, let's write down first of all like this. So, and cosine of 0 is 0, so and this value equals 0. So, here we will receive that, so this series multiplied by 4 equals minus this value, b squared over 3. So, minus n minus 1, sorry. So here is, okay. So if I want, okay, let's write like this for now. So received the following expression. Then let me move 4 from the left part to the right. Okay, I will receive here minus b squared over 12. But what do we see here? That here we have minus 1 in power of n minus 1. So let's multiply this both parts of the equation by 1 or by minus 1. So we receive the following stuff. So sum S1 equals p square over 12. So calculated sum of this series. And what about S2? So which equals so the generalized harmonic series with power over 2. So how we will receive it? Let's calculate value of f at point of p. So f from p, so it will be equal. So p, here I receive cosine of Pn, and cosine of Pn actually equals minus 1 in power of n. I lost this part, sorry. So then cosine of Pn equals minus 1 at point n. I will write everything in details here, just not to lose no anything. So if I multiply this minus 1 and minus 1 in power of n, I will receive 2n. And actually minus 1 in power of 2n will be equal 1, of course. And we remember that we calculate f from p, and f from x equals actually x squared. So all this stuff equals p squared. So now let's let's solve this equation with respect to the series, to the sum. So S2, let's do like this. So for S2 equals 2p square over 3. Then S2 equals uh, p square over 6. So that's the sum that we received. Let me check with my notes. Yeah, so the first series p square over 12 and the second p square over 6. Any questions about this exercise?
Sorry, I have a question.
Yeah.
When we say that f of pi, why do we say that it equals to pi square? Why
Uh,
do we assume this?
f from p, why it equals p square?
Yeah, yeah.
Because the function is f from x equals x square. So that's why,
Ah,
yeah. Don't
that's why.
forget about the expression for the function that is given initially.
Oh, okay, okay.
Yeah, please be attentive. Um,
Yeah, thank you for the explanation.
yeah, more questions? Okay, if no questions, let's have a break for 5 minutes, and after that, we will continue uh, solving tasks related to Fourier series. Let's continue. So having the following task. So we have to expand the function f from x equals p minus x into Fourier series in terms of cosines and in terms of sines. So what does it actually mean? So in terms of cosines mean that we will continue the function. We will continue the function in even way. And in terms of sines means that we will continue the function in odd way. And x here is defined so from 0 to p. So we will continue first of all when expanding in terms of sines, or if in terms of cosines, we will continue it in even way. So how it will look on the graph? So it looks in the following form. So like this. So this curve actually is p minus x, and this is so then it's how we continue it in even way. And after that, we continue it periodically with the period of 2p. So then how we will calculate the coefficients of the Fourier series? We will calculate only a0 and an so bn will be equal to 0 because we expand in terms of cosines. So we will calculate by the following formulas. So we will integrate from 0 to p, and here will be 2 instead of 1, so 2 over p. So calculating this integral. So what do we receive? 2 over p. So px minus 1 over 2x square with the substitutions from 0 to p. So from 0 to p, if I substitute 0, this expression will be equal 0. So what do I have here? So 2 over p, and here p square minus 1 over 2 minus 1 over 2 p square. So what I receive, 2 over p by p square over 2. So it equals p. And what about an? Not alpha, but a. So then we will multiply it by cosine of nx. And this expression will be integrated by parts. So u equals p minus x. Du equals minus dx. dv equals cosine of nx dx. Then v equals 1 over n sine over nx. Okay, calculating the integral. So 2 over p. So first of all, writing down uv product with the substitutions from 0 to p. minus 1 over n integral over, so from 0 to p, integral of sine of nx dx. Let's look what do we have here. This expression will be equal 0 because we have sine of Pn and sine of 0. So how it will be simplified? So we will have minus 2 over Pn. And this integral. Then calculating this integral, we will receive 2 Pn square multiplied by cosine of nx with substitutions from 0 to p. So 2 Pn square multiplied by minus 1 in power of n plus minus 1. And what it will be equal. So if n is even, we will have, so here we will have 0. And if n is odd, we will have minus 4 over Pn square. So if n equals to k minus 1. Received coefficients for Fourier series. So it will be equal the following. So f from x equals s from x. So a0 over 2. So p over 2. So p over 2. And minus so sum from n from 1 to infinity. So 4 over p n 2n minus 1 square, and multiplied by cosine over 2n minus 1 x. Also, let's move constants out of the sum to simplify this expression. So moving 4, moving p. And we received the following expansion in terms of cosines. Any questions about this part? So part A, actually it was. Okay, if no questions, let's solve part B. So we will expand in terms of sines. When expanding in terms of sines, we will continue function f from x in odd way. How it will look graphically so it will look like this. So the symmetry is with respect, the symmetry with respect to beginning of coordinates. So this function is odd, and it has yeah. So if the function is continued in even form, it has no discontinuity points. But here we have discontinuity points at points 2 p.m. So let's calculate Fourier coefficients for these terms. So how it will be calculated? So an will and so a0 and an will be equal to 0, and we will calculate only bn. So we will have the following integral. So from 2 to p. So 2 over p from 0 to p. Sorry. And integral p minus x multiplied by sine of nx dx. So again, integrating by parts. So u equals p minus x, du equals minus dx. I hope that I didn't lose signs. I lost signs somewhere. But yeah, so the result here, yeah, so here must be plus before the sum, so it was my bad. Okay, so du equals minus dx, then dv equals sine of nx dx, so v equals minus 1 over n cosine of nx. So received the following expression. So first of all, multiplying u and v. Yeah, let's move p minus x here. And substitutions from 0 to p. And minus, yeah, because minus here, and minus before integral. So minus integral from 0 to p. And 1 over n cosine of nx dx. So let's calculate, let's simplify. Okay, let's start calculating. So here, if I substitute p, I will receive 0. So p minus p will be equal 0. And what about 0? If I substitute 0, I will have so here will be 1, here will be p, and we also subtract this part, so it will be 1 over n. So p over n. So received this part. And what about this integral? So it will be equal 1 over n square sine of nx with the substitutions from 0 to p, which will obviously equal 0. So this stuff will be equal 0. So we will receive 2 over n. Let me check my notes. Yeah, 2 over n, so it's okay. And received the sum of, so the sum of, okay, f from x will be equal the following stuff. So n from 1 to infinity, 2 over n multiplied by sine of nx. And also I will move 2 out of the sum. So received the following Fourier series in stop y so n square. Let's go yn square. That's a mistake. Okay. N in power of 1 must be. So sine of nx over n. And what about, and it equals s from x when x from minus p to p exclusively. Stop, from 0 to 2p. And what about s at point 0? So this sum will be equal f from plus 0 plus f from minus 0 over 2. And let's look at the graph. So f from plus 0 equals p, and f from minus 0 equals minus p. So it will be equal p. Stop. Why? Mm. Yeah, p, yes. Stop. Here will be p, and here minus p. So it must be equal to p. Yeah. So it's not correct as well. I don't know why. Yeah, maybe copy and paste mistake. So it will be equal p. Any questions about this exercise? Okay, if no questions, let's move to exercise 4. So, what do we have here? So here we have the function that is given graphically, and we need to expand it into Fourier series. So first of all, let's define, so looking at this graph, let's define the expression for the function, so analytical expression. This function as well is given piecewise. So what can we see here? By the way, this function is periodic and it has period from minus, so from minus 2 to 2, then it continues. So not 2p periodic, but 2l periodic. Let's start from the easiest part. So when a function equals 2, so it equals 2 when x from 0 to 2. And what about from minus 2 to 0? It seems that we have the angle coefficient 1 over 2. And yeah, it also so it is shifted up in by one cell, so it equals 1 over 2x plus 1 over 2x, not 1 over x, so 1 over 2x plus 1. So, and x from minus 2 to 0. So received such analytical expression. And now let's look at these formulas. So for trigonometric Fourier series for 2L periodical functions. So it is similar to p periodical functions. Here just so here p so we substitute p instead of L, and we receive such uh, simple expressions. And here we have in argument of cosine p n x over L and sine of p n x over L. And when calculating integrals as well, argument over cosine and sine is changed, and we also divide by 1 over L. So the period here, L equals 2. 2L, yeah, so actually 2L equals 4 and L equals 2. Okay, let's calculate coefficients. So A 0, uh, okay, yeah, A0 equals, so 1 over 2, integral from minus 2 to 2, f from x dx, so it will be equal 1 over 2 integral of so from minus 2 to from minus 2 to 0, this expression will be and mm, now it's okay. And what about from 2 to 0? So 2 dx. From 0 to 2, sorry. So 1 over 2. And now calculating the integral. So what I received here, 1 over 4x squared plus x with substitutions from minus from minus 2 to 0. And plus 2x with substitutions from minus 2 to 0. Oh, well, from 0 to 2. So if I substitute 0 here, I will receive 0. And what I have, 1 over 2. If I substitute minus 2, so here 4, so I have a 1. By the way, sorry, minus 1. Yeah, so because I'm subtracting, so the lower limit. So minus 1 plus 2, and here will be 4, so plus 4. So I receive 5 over 2. So received A0. And what about AN? So moving to AN. 1 over 2 cosine of PNX over 2 dx. So multiplying all this stuff. And this integral will be calculated by parts. So calculating. So u equals this expression. Du equals 1 over 2 dx. Dv equals and what about substituting cosine? So dv will be equal this cosine, and v will be equal 2 over pn sine over pnx over 2. So it seems that everything is taken into consideration, so calculating integrals. So 1 over 2, and what do we have? So first of all, multiplying u and v. Okay, this part done. So from -2 to 0. And minus, so multiplying these parts. 1 over Pn, integral from sine of Pnx over 2. And what about this integral? So we will have plus plus 4 over Pn multiplied by sine of Pnx over 2 with the substitutions from 0 to 2. And now let's see what we will receive. So what can we simplify here? So here, because of sine, so we have sine of 0, sine of Pn. Yeah, so if I substitute x here, I will receive so if I substitute 0, I will receive sine of 0. If I substitute -2, I will receive sine of -Pn. So this part goes away. And this part goes away as well, because I will receive sine of Pn and sine of 0. So I will have only this integral. So -1 over 2 Pn this integral. And now let's calculate it. So -1 over 2 Pn yeah, so okay, 2, so let's move minus out because we have minus cosine. 2 will be cancelled as well, so we have p square and n square. Well, cosine of pnx from -2 to 0. And what we will receive? So we will receive 1 minus, and if I substitute -2, I will receive cosine of Pn, so 1 minus 1 in power of n. And how to simplify this expression? So if n is even, it will be equal 0. So 0 if n equals 2k. And it will be equal it will be equal to over p square n square if n is odd. Let me check my notes if the coefficient is calculated correctly. Yeah, it is correct. And now let's move to b. So an is done. calculating Pn. Okay, I will substitute, I will replace cosine with the sine. And after that, we will calculate so we will calculate this integral by parts. So u equals, so this integral will be calculated by parts, and this integral is a table integral. So u equals this expression, and du equals 1 over 2 dx. Dv equals sine of pnx over 2 dx. V equals minus 2 over Pn cosine of Pnx over 2. And now let's calculate, let's substitute everything and look what can be simplified. So first of all, uv with substitutions from -2 to 0. And then minus, stop, plus 1 over Pn integral from -2 to 0 cosine of Pnx over 2 dx. So done with this integral, and now substituting and now calculating this integral that we have. So minus 1 over Pn cosine of Pnx over 2 with the substitutions from 0 to 2. And let's look what can we simplify here in this expression. So 1 over 2. So if I substitute 0, I will have okay, what we will receive. Yeah, and by the way, I can move Pn out of brackets, so let's do it first of all. So Pn will be moved out of brackets and will look much more simpler. So it's better. And now let's continue calculations. So if I substitute 0 here, it will be 1. And here will be 1. So, yeah, duplicated. So here it will be, so -2 multiplied by 1 minus, and if I substitute 2 here, I will receive 0. So just -2 instead of this huge expression, -2. What about this integral? So it will be equal 2 over Pn 2 over Pn sine over Pnx over 2 with the substitutions from -2 to 0. And it obviously will be equal 0. And what about cosine of p and x over 2? So if I substitute here minus, if I substitute 2, I will receive minus 1 in power of n. And if I substitute 0, I will receive 1. Now let's rewrite it a little bit. So it will go away. And now expanding these brackets. So minus 2, okay, plus 1 and plus, let's write down minus 1 in power of n plus, in power of n plus 1. So let's do like this. Or what we not do like this. Okay. So we have the following expression. And after that, we will expand brackets. So here will be minus 1 in power of n. Here will be plus 1. So 1 over 2pn, and here will be 1. Oh, okay. Minus 1 in power of n plus 1, and minus 1. And let me check this substitution. Let me check this answer here. Stop, y2. So something was wrong. Something was lost. So one, okay, let me check with notes. So this expression minus 2pn, yeah. Stop. Yeah, I was 2 here. But anyway, it will not stop. No, mistake is here. Oh, I see. Yeah. So actually the answer, so the coefficient is correct. And let's look what or not. Just a moment. Let me recalculate it, because it seems that something is not okay. So yeah. Yeah, so I lost 2. Actually, it everywhere must be. Yeah. So oh, okay. But no. No, no. Okay, let's check here. So 1 over 2. So 1 over 2 here. And with integration by parts, what do we have? So yeah, so minus here, so it must be, so here it must go away. And I lost, no, I didn't lost here. anything. So it's okay. Yeah, actually the answer must be like this, so Bn. And that's how the sum looks like. Yeah, so An and A0 are correct. Bn, I need to recheck. So this series is the following. So I substitute An. So actually I will write like this in this form. It will be written in this form because we have no such alternating signs. So yeah, we have alternating sign here for Bn, but it will not turn the expression to 0. So we will receive the following Fourier series. And for discontinuity points, calculated that at point plus minus 2n, it equals 1. And at point 0, it equals 3/2. Any questions about this exercise? About the whole lesson? About previous lessons? Okay, if no questions, we will finish. So it was a pleasure to work with you during this year. I wish you to pass your exams successfully and continue studying on the second course. And so thank you for your attention. Goodbye. Have a nice day. Stay safe.
Thank
Thank
you.
you very
Goodbye.
much.
Thank you. Goodbye.
Thank you
Have
a
a nice
lot.
day.
Take care.
Goodbye. Take a nice
Goodbye.
Thank you for your lessons. See you next time.
Yeah, see you.